Today, what we're going to do for the rest of this lecture is going to be analyzing this system with control volumes. And after we do this, you're going to have a newfound appreciation for resistance networks, I promise you. So what we have then is the Pyrex and the silicon dioxide. And we have the flux that goes through the system. And so we can set up a few control volumes. In fact, we need two separate control volumes for this case. We have to make sure that this control volume is thin in the direction of transport. This is one thing I'm going to keep saying and keep saying and keep saying. And we're going to try to take a look at this now. So this transport is in Y. And so I need to make sure this is thin in delta Y. Thin in Y, so I'll make it a delta Y. Excuse me. And in this case, I'm going to let this also be a delta X and a delta Z. So this is the same control volume we set up previously. What I'm also going to do is set up a control volume that's the entire surface area. But I'm going to make sure that it's really thin. In fact, in Y. So what I've said is that you need to make sure this volume is really thin in the direction of transport. So I'm going to do that with the SiO2. With the Pyrex, I'm going to go through the same derivation that we've already seen. So here, this volume for the SiO2 is going to be the surface area, a large surface area, times delta Y. The volume for the Pyrex is going to be delta X, delta Y, delta Z. And we're going to carry out two simultaneous derivations in parallel to figure out what the profile is through this system. So again, what we'd like to know is how does the concentration look? We know we assume no jump discontinuity, so that's one thing that you can actually have in mass transport. We're assuming no jump discontinuity, so we have the concentration of helium at the bottom is very high, and we have a zero concentration at top. Based on what we know about diffusion coefficients and how we just talked about this system, and actually this was what question I left you with right before we left for spring break, was what the slopes of these would look like. And we realized that this should probably have a much steeper slope, and this should probably have a less steep slope, shallower slope. And that was based on us doing a kind of thought game, a thought process on where we would expect the bigger change in concentration, whether the thing with the higher diffusion coefficient or the lower diffusion coefficient would cause a greater or lesser difference in concentration. And of course, we figured out that the greater the diffusion coefficient, the lesser change in concentration we would expect. And so this was kind of exactly where we left off. Right, and then based on Einstein's theory, he said, well, I look at this driving force as this push. It's a literal like pushing force down the slope. So what he means is we're going this way. We're sliding down the slope of concentration, and this is our chemical potential gradient. All right, so we need to carry out now two simultaneous derivations. One, we're going to use this finite control volume. One, we're going to use a large control volume, but it's very thin in our direction of transport, and we're going to see where this leads us.